You know, it's pretty wild when you think about it. Most of the universe is totally invisible. We're literally swimming in a sea of energy right now, from the radio waves bringing music to your car to the microwaves that heat up your lunch. Today, we're going to peel back the curtain and really dig into the amazing science behind all of these invisible waves.
So here's our game plan. We'll start with a game-changing idea that first tipped us off to the true nature of light. Then, we'll dissect a wave to see what it's made of, explore that huge family called the electromagnetic spectrum, and even get our hands on the simple math that ties it all together. After that, we'll see it in action before we wrap up with the big takeaways.
All right, to really get this, we've got to hop in a time machine and go back to the 19th century. A massive debate was raging about what light is, and the answer was about to change everything.
I mean, this was a huge deal. For centuries, pretty much everyone, following the legendary Isaac Newton, believed light was made of tiny little particles. But then, in the 1870s, James Clerk Maxwell proposed something totally different. He said light was actually a wave, a ripple of electric and magnetic fields. It was an incredible theory, but it was just a theory, until Heinrich Hertz actually proved it in the lab, creating and detecting these invisible waves. Just like that, our understanding of the universe was flipped on its head.
Okay, so if light is a wave, what does that actually mean? What are the moving parts? Let's zoom in and take a look at the anatomy of one of these things.
This is really the heart of it all. Picture a wave moving forward, along that x-axis. As it goes, you have an electric field that's oscillating up and down. But at the exact same time, you have a magnetic field that's oscillating side to side. They are perfectly in sync, and, this is key, they're always at perfect right angles to each other, and also at a right angle to the direction the wave is moving. It's this beautiful, perfectly choreographed dance between electricity and magnetism that is an electromagnetic wave.
And here's the part that's truly mind-bending. Think about waves in a pond. They need water. Sound waves need air. But these electromagnetic waves, they don't need anything. They can travel through the total emptiness of outer space, no problem. And no matter what kind of wave they are, radio, X-ray, visible light, they all travel at the exact same speed in a vacuum. The ultimate cosmic speed limit, the speed of light.
So we've got this basic wave structure, this building block, but it's not just one type of wave. It turns out this single design is the blueprint for a massive, diverse family of radiation. We call it the electromagnetic spectrum.
And here is the whole family photo. Way over on the left, you've got your super high-energy gamma rays. Their waves are packed super close together, high frequency, short wavelength. As we move to the right, the waves start to stretch out. The frequency goes down and the wavelength gets longer. We move through X-rays, ultraviolet, and then, there it is, that tiny little slice of visible light, followed by infrared, microwaves, and all the way to radio waves, whose wavelengths can be as long as a football field or even bigger.
But just look at this. This is what our eyes can actually see. It's this impossibly small sliver of the whole spectrum. Every color you've ever seen, from deep violet to bright red, is crammed into this tiny window. It's a pretty humbling reminder that our eyes are only showing us a tiny fraction of what's really out there. Now, this might all seem incredibly complex, but the way scientists actually describe and predict all this stuff, well, the math behind it is surprisingly straightforward and, honestly, pretty elegant.
Okay, first up is frequency. Imagine you're standing still and a wave train is going past you. If you just count how many wave crests pass by you in one single second, that's it. That's the frequency. We measure it in hertz, named after the guy who proved these waves were real.
Next is wavelength, and this one is exactly what it sounds like. It's just the physical distance from the peak of one wave to the peak of the very next one. It's a length, so we measure it in meters. Simple as that.
And here is the magic formula that connects them. The speed of light, c, is a constant. It never changes. This simple equation shows us that frequency and wavelength are on a cosmic seesaw. They are inversely related. If you have a really high frequency with waves bunched up tight, the wavelength has to be short. If you have a really long wavelength, the frequency has to be low. They are locked together in this perfect, simple relationship.
All right, there's one more term you'll see, especially if you get into a field like spectroscopy, which is all about how light and matter interact. It's called the wave number. It sounds complicated, but it's just the inverse of the wavelength. It's basically asking how many full waves can you fit inside 1 centimeter. It's just a different way to look at the same thing.
Okay, so the theory is cool, but let's make this real. How does this mathematical toolkit help us understand the waves that are all around us every single day?
So let's take a radio station. Say it's broadcasting in a frequency of 1368 kilohertz. We just have to rearrange our little formula to solve for the wavelength. We take the speed of light and we divide it by the frequency. And of course, we have to make sure our units match up, converting kilohertz to hertz. And what do we get? A wavelength of 219.3 meters. That's longer than 2 football fields, a classic radio wave.
Now let's do the same thing, but for visible light. We know the wavelengths are crazy small, from about 400 to 750 nanometers. When we plug those tiny numbers into our equation, the result is, well, it's just astounding. Our eyes are sensitive to frequencies between 400 and 750 trillion waves hitting them every single second. It's almost impossible to wrap your head around that.
Okay, one more, just to bring it all home. Let's look at yellow light. Its wavelength is about 5,800 angstroms, another super tiny unit scientists use. First, we convert that to meters. Easy. From there, we can find its wave number. And then, using our main equation, we can find its frequency. See? With just these few tools, we can describe pretty much any wave in the universe.
Wow, okay, we've covered a lot of ground here, from 19th century physics to some pretty fundamental math. So what are the big things you really need to remember from all this?
When you boil it all down, it's actually incredibly simple. The whole universe of electromagnetic radiation runs on a few basic rules. You have one critical constant, the speed of light, you have two simple equations that connect everything together, and you have one big family, the spectrum, all built from that same dancing pair of electric and magnetic fields. This is the toolkit. This is what lets us understand everything from the longest radio waves to the shortest gamma rays. Which leaves us with a final and honestly a kind of unsettling question. We've just spent all this time building up this perfect, logical, beautiful picture of light as a wave. It explains so much. But what if that's not the whole story? Because later experiments showed something that seems impossible, that this very same radiation can also act like a particle. And that one baffling fact is what throws open the door to the truly strange and wonderful world of quantum physics.